The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So, over the last few lectures, we have talked about coherence within an atom, coherence between two levels, coherence between three levels. And today, in the last class, we want to talk about coherence between atoms. So this is now, I think, for the first time in this course, where we really have more than one atom. Well, maybe we discuss some collisional broadening, or we discuss the van der Waals interaction between two atoms, but usually atomic physics is one atom at a time. But now we want to understand one important phenomenon which happens when we have many atoms. And the phenomenon is called superradiance. So I left something good for the end. And superradiance has in common the word super with superconductivity and superfluidity. And it really represents that the atom, many atoms act together, and the word super also means coherence among atoms. Superfluidity and superconductivity have a macroscopic wave function where all the atoms, the matter waves, are coherent. The phenomenon of superradiance, as we will see, has not so much to do with coherent atoms, it has more to do with coherent photons. So it's more, some people regard superradiance as a laser without mirrors. But you'll see where the story leads us to. So just to set the stage for many atoms, we should first talk about single atoms, and all that is described in this landmark paper by Dickey in 1954, which is posted on our website. So if you have a single atom prepared in the excited state, it decays to the ground state, and we want to characterize the system by an emission rate as a function of time. So the emission rate initially is gamma. Gamma, the natural line width of the excited state. And then, of course, the emission rate decays because we don't have any atoms left. Similarly, the probability to be in the ground state is 0 initially. And then, with an exponential approach, it eventually goes to unity after a while, after we have only atoms in the ground state. So this is rather straightforward. But now we want to bring in a second atom, and I'm asking, what happens when we have not one atom, but two atoms? One is in the ground state, one is excited. So pretty much what we have added to the original situation with one excited atom was we have brought in one ground state atom, which naively you would think does nothing. But that's not the case. What happens is when we, I assume just for, we will drop the assumption later, but we assume for now that all the atoms are within one optical wavelength. What we then realize is for two atoms, and I will show you that in its full beauty, that the initial rate of light which comes out of the system is the same. So the extra ground state atom does not change the initial emission rate, but it goes down faster. And if we ask what is the probability that the atom is in the ground state, we find that it's only 1/2. So in other words, normalized per system, we have a ground and excited state atom, and what comes out is only half a photon. Half of the atoms do not decay. So it's not the same rate and the same decay. Something profoundly has happened. And this is what we want to understand. So let me give you the correct answer. So the rate of emission as a function of time for the situation. We start out with gamma, but then the emission decays not with gamma but with 2 gamma. And the probability that both atoms are in the ground state, or that the second atom, so to speak, is in the ground state, will only asymptotically go to 1/2. And it does so exponentially, but again with a time constant which is 2 times faster than for the single atom system. So we have the same initial emission rate, but only a probability of 1/2 to emit at all. So in order to understand it, we have to look at an atom in the excited state, an atom in the ground state, and we want to write down the wave function as a superposition of a symmetrized and anti-symmetrized wave function. And I should tell you, I'm going very slowly for 2 atoms. And then, once I've introduced the concept for 2 atoms, with a few pen strokes, we can immediately discuss n atoms. So all the physics, all the understanding, what goes on in superradiance is already displayed for 2 atoms. So we want to have a superposition of symmetric and anti-symmetric wave function. The symmetric one is the normalized wave function, which is GE plus EG. And we call that the superradiant wave function for reasons which will become clear in a moment. And if we have a minus sign here, the antisymmetric combination we call the subradiant wave function. Now, what happens is we have to consider, so we have symmetrized the wave function. Well, I didn't really tell you why, but it's always good to symmetrize. Symmetry is, if you can use it, something good. And the reason why I symmetrized it is because I want to look at the interaction Hamiltonian. And if I look at the interaction Hamiltonian, the one we have seen many, many times, but now for 2 atoms, we will immediately realize that this interaction Hamiltonian is symmetric. So therefore, if the Hamiltonian is symmetric, it's really a good starting point to have the wave function for the atoms expanded in a symmetric basis. And since I want to emphasize that the whole story I'm telling you today has nothing to do with the kind of second quantization, well, it is about spontaneous emission, but it's not involving any subtlety of spontaneous emission, and field quantization. I want to sort of write down the interaction Hamiltonian both in a classical and a quantum mechanical way. In the classical way, we have the dipole moment E1, D1, we have the dipole moment D2, and the atoms talk to the electric field at position R and T. But since we assume, and now you realize where the assumptions, some of the assumptions are important, since the atoms are localized to within a wavelength, they really talk to the same electric field. There are no phase factors. In about 55 minutes or so, we introduce phase factors for extended samples, but for now we don't. And therefore, what the atoms couple with is with a dipole moment, which is the sum of the 2 dipole moments. So this is classical or semi-classical. But so what enters in the Hamiltonian is only the sum of the operators for the two atoms. And the same happens in the QED Hamiltonian. And actually, I will get a little bit more mileage out of the QED Hamiltonian, as you will see in a moment. Because with the QED Hamiltonian, we describe the atomic system by, first atom 1, with the raising and lowering operator with the atoms interacting with A and A dagger. And then I have to add the term where the index 1 and 2 are exchanged. So we are introducing here, it's convenient for two-level atom, the spin notation. Sigma plus and sigma minus are the raising and lowering operator, which flip the atom from the ground to the excited state and vice versa. But the important part now is, and this is where everything comes from in superradiance, that the coupling involves not the individual spins, little sigma plus and sigma 1 and sigma 2, it only involves the sum of the individuals, I equals 1 to 2, and later we extend the sum to n. So therefore, what matters for the interaction of the atoms with the electromagnetic field is the sum of all the atomic spin operators. And the sum is, of course, symmetric against exchange. So therefore, when we are asking what is the coupling of the state which I called the superradiant state, the one where we had symmetrized EG plus GE, or we ask what is the coupling of the subradiant state to, well, the state where both atoms are in the ground state. Well, now we can use symmetry. The left-hand side is symmetric, the operator is symmetric, and now only the symmetric state will couple, the anti-symmetric state will not couple. So therefore, the subradiant state, EG minus GE, cannot decay. That's why we called it subradiant. Well, I think a better word would be non-radiant, but non is definitely subradiant. And for the matrix element EG and GE, we find that we have actually an enhancement of the coupling by a factor square root 2. So now we pretty much know what we have to do. We want to use the symmetry of the symmetry. We consider ground and excited state of each atom as spin 1/2. But now we want to look at the total spin, the total pseudo-angular momentum of the two atoms, and later we extend it to n atoms. So we want to use now the power of the angular momentum description, and that goes like follows. We have 4 states of 2 atoms, and this is GG, GE, EG, and EE. And if I denote with ground state spin down, excited state spin up, I'm talking about 2 spin 1/2 states. And 2 spin 1/2 states can couple to S equals 1, total S equals 1, and total spin S equals 0. And that's what I've done here. I have arranged the states EE, the symmetry superradiant state, the ground state, and the subradiant state. I've arranged an energy level diagram. Here we have 0 excitation energy, here we have 1 excitation energy, and here we have 2 excitations energies of the atom. But I've also labeled now the spin labels for the combined system. Those symmetrized states correspond to a spin equals 1. It's a triplet ladder with 3 different magnetic quantum numbers. M equals +1 means everything is highly excited. M equals -1 means we are in the total ground state. And here we have the singlet state, which is the antisymmetric state or the subradiant state. And our interaction Hamiltonian is the total spin plus minus. It is the raising and the lowering operator. And you know that the raising and lowering operator for the spin is only making transitions within a manifold of total S. It just changes the M quantum number by ±1. So the Hamiltonian cannot do anything to the singlet state because there is no other singlet state to couple. But within the triplet manifold, the sigma plus, sigma minus operator is creating transitions between the different M states. And the coupling constant, which for an individual atom was little g, is now factor of √2 enhanced. And we will see in a few minutes that for n atoms, it's √n enhanced. And if n is big, that's where the word super in superradiance comes from. Yeah, actually, let me just quickly add the diagram for the single atom. The single atom has only an excited state, a ground state. It corresponds to S equals 1/2. And we have magnetic quantum numbers of +1/2 and -1/2. And the coupling due to the light-atom interaction goes with the coupling constant G. So the key message we have learned here is that we should, when we have several atoms within an optical wavelength, we should use for their description symmetrized and antisymmetrized states. Or when we generalize to more than 2 atoms, we should just add the total angular momenta by treating each atom as a pseudospin 1/2. And it is this angular classification which tells us how the radiation proceeds, because the coupling to the electromagnetic field is only involving the lowering and raising operators for the total spin, and this only acts on a manifold where the total spin S is conserved, and what we get is transitions with delta M plus -1. So question is, have those effects been observed? Yes, they have actually, and they're important for a lot of research, but just for 2 atoms, the simplest observation is when you take 2 atoms, let's say 2 sodium atoms, bring them very close, and you form a sodium 2 molecule. And to some extent, when the molecular binding is not, for states where the molecular binding is not completely changing the electronic structure, we can regard the sodium 2 molecule as consisting of 2 sodium atoms. And indeed, if you do spectroscopy of the sodium 2 molecule, you find some molecular state which are very long-lived, like the subradiant states, which do not radiate at all, but then you find states which have a spontaneous emission rate, which is about 2 times faster than the atomic spontaneous emission rate. So you find sort of that you can understand some radiative properties of molecules by assuming that their related to the sub and superradiant state of the two atoms which form this molecule. So an example here is sodium 2 molecule. Has states with where the gamma molecule is approximately 2 times gamma sodium, or other states where it's very small. Okay, now we understand the basic of superradiance in two atoms, and therefore we can now generalize it to n particles. But before I use the spin algebra to describe n particles, I want to glean some intuition where we just consider, and this takes us back to the beginning of the course, where we consider n spins in a magnetic field. So and I really invite you to think now completely classically. We describe it quantum mechanically in a moment, but I've often said in this course, if in doubt, if you have a classical description and a quantum mechanical, and they seem to contradict, usually there is more truth in the classical description. It's so much easier to fool yourself with the formalism of quantum mechanics. So let's take n spins in a magnetic field and ask what happens. So we have n spins. So these are now real spins. They have a real magnetic moment. These are tiny little bar magnets. And we do a pi over 2 pulse. And after we've done a pi over 2 pulse, the spins are aligned like this. Let's assume we had our magnetic field. And now what happens is these spins will precess at the Larmor frequency. So now you have your n spins, they precess together. And if you have a magnetic moment which oscillates, the classical equation of electromagnetism tell you that you have now a system which radiates. But compared to a single atom, the dipole moment is now n times the single atom dipole moment. So therefore, what do we expect for the radiated power? Well, if the radiation, electromagnetic radiation by an oscillating electric or an oscillating magnetic dipole moment scales with the dipole moment squared. So therefore, we would expect that the power radiated is proportional to n squared. And that means, I have to take the factor of n now apart, this means this is n times higher than if you assume you have n individual particles and each of them emits electromagnetic radiation. So what I'm telling you is if you scatter n spins through your laboratory, you excite them, pi over 2 pulse, they radiate a power which is proportional to n. But if you put them all together, localize them better than the wavelengths, their radiated power is proportional to n squared, which is an n times enhancement. So the way how I put it for n spins, and this is a situation of nuclear magnetic resonance, this is the completely natural picture. But if I would have asked you the question, let's take n atoms which are excited and put them close together, you say, oh, well, each atom does spontaneous emission, and if you have n atoms, we get, n times the intensity. You would have gotten a different result. So we are so accustomed to look at spins in NMR as a coherent system, look that all the spins add up to one giant antenna, to one giant oscillating dipole moment, whereas for atoms, we are so much used to say each atom is its own particle and does its own thing. So for n excited atoms, they are usually regarded as independent. However, and this is the message of today, that there shouldn't be a difference. All two-level systems are equivalent. Side remark, for NMR and spins, it is much, much easier to observe the effect because the condition that all the spins are localized within one wavelength is always fulfilled if the wavelength is meter or kilometers. But if you have atoms which radiate at the optical wavelengths, this condition becomes non-trivial. That is partially responsible for the misconception that you treat the two-level system, which is a spin, in your head differently from the two-level system, which is an atom. So the important difference here is lambda. And we have to compare it with the sample size. And usually the sample size is much larger in the optical domain and is much, much smaller in the NMR domain. However, and that's what we will see during the remainder of this class, some of the dramatic consequences of superradiance will even survive under suitable conditions in extended samples. So when we have samples of excited atoms much, much larger than the optical wavelengths, we can still observe superradiance. So therefore, for pedagogical reasons, I first completely focus on the case that everything is tightly localized. We derive some interesting equations, and then we see how they are modified when we go to extended samples. But I want to say the intuition from spin systems, the intuition from classical precession and nuclear magnetic resonance will help us what happens for electronically excited atoms. So we want to use this other spin 1/2 system as a powerful analogy to guide us. So before I start with the angular momentum formalism, I want to emphasize that what are the ingredients here? Well, we're talking about coherence, coherent radiation, coherence between atoms, and we talk about radiation. And the important part here is the following, that when we talk about radiation, we have the situation that all atoms interact with a common radiation field. In other words, all the spins, all the atoms have to emit their photons into the same mode of the electromagnetic field. And therefore, you may be right in some limit that the atoms are independent, but not the photons they emit. They go into the same mode. And therefore, the emitted photons cannot be treated independently. And and that's why the classical picture is so powerful for that, because in the classical picture, we do a coherent summation of the field amplitudes. So we have constructive interference, the superposition principle of field amplitudes, built into our equations and deeply imprinted in our, deeply engraved in our brains. And that's why when we use classical arguments, we automatically account for that the photons sort of interfere, that the photons are emitted into the same mode of the electromagnetic field. And eventually, this leads to the phenomenon that we have coherence and enhancement when we look at spontaneous emission for n atoms which are sufficiently localized. So let me also discuss what we have assumed here. Number one is we have assumed we have a localization of the sample smaller than the optical wavelengths. The other thing, and this is really important, we're talking here about a collective phenomenon where n atoms act together and do something in a, they develop the phenomenon of superradiance. They decay much, much faster than any individual atom could do by itself. But nevertheless, we have not assumed, or we have actually excluded in our description, that there is any direct interaction between the atoms. The atoms have no van der Waals interaction, they're not forming molecules, they're not part of a solid with sort of shared electrons or so. The atoms are, in that sense, non-interacting, and therefore, in a way, as long as they are just atoms, independent. Finally, and I want you to think about it, you can think about already for two atoms, before we generalize it to n atoms. Think about it, what was really the assumption about the atoms? Do the atoms have to be bosons to be in this symmetric state? Do they have to be, can they be fermions? Or can they be even distinguishable particles? If the two atoms were, one would be a sodium atom and one would be a rubidium atom, but let's just say we live in a world where sodium and rubidium atoms emit exactly the same color of light. Would we have then sub and superradiant state for two atoms, one of which is sodium and one of which is rubidium? Yes?
Isn't the fundamental assumption that the photons have to be with respect to the image?
Exactly.
As long as that's satisfied.
Yes, it is really, and that confuses many people, it is the indistinguishability of the photons they have emitted. It is the common mode where the photons are emitted. The atoms can be distinguished. I mean, also, we've made the assumption that the atoms are localized to within an area which is much smaller than lambda. But you could imagine you have a solid state matrix and you have one atom here, one atom there, and you can go with a microscope and distinguish them. So therefore, the moment you can distinguish them because they are pinned down in a lattice, or if you don't like a lattice, take two microscopic ion traps a few nanometers apart and you tightly hold on to two ions. It doesn't matter whether they are bosons or fermions. It only matters whether you have bosons or fermions when the atomic wave functions overlap and you have to symmetrize it. As long as you have two atoms which are spatially separated, it doesn't matter whether they are bosons or fermions. And that also means they can be completely different atoms. You can already call it boson A, boson B. Now you can call it sodium and rubidium. And they can have different numbers of nucleus. They can have different numbers of neutrons in their nucleus. They could be different isotopes of the same atom. The whole collective phenomenon comes when they emit a photon into the same mode. Okay, so now we want to do a formal treatment for n particles. So we have now the individual pseudospins 1/2. We perform now a sum over all n particles. We get the total spin s. The total spin s quantum number has to be smaller or equal than n over 2 because we have n spin 1/2 systems. The m quantum number is 1/2 times the difference of the atoms which are in the excited state minus the atoms which are in the ground state. And this is, of course, trivially must be smaller than s, because m is the z component of s. And we are now describing the system by the eigenstates s and m of the collective spin. So that means we have the following situation. We have a manifold. We want to show now all the energy levels. We have a manifold which has the maximum spin n over 2. The next manifold has n over 2 minus 1. And the last one has, let's assume we have an odd number of particles, s equals 1/2. So here, we have now n energy levels. We can go from all the n atoms excited to all the n atoms being de-excited. In the following manifold, we have s is 1 less, and therefore we have a ladder of states which is a little bit shorter. And eventually for s equals 1/2, we have only two components, plus 1/2 and minus 1/2. So those levels interact with the electromagnetic field. The operator of the electromagnetic field, we have already derived that, involves the sum of all the little sigma pluses, sigma I pluses, and we call the sum of all of them S plus and S minus. And the matrix element is now for spontaneous emission, you have a state with Sm. S minus is the lowering operator for the n-particle system, so it goes from a state with a certain number of atomic excitations to one excitation less, and that means this is the act of emitting spontaneously one photon. The operator S minus stays within the S manifold, so we stay in the same ladder which is characterized by the quantum number S, but we lower the M quantum number by 1. The M quantum number is a measure of the number of excitations. And we know from general spin algebra that this matrix element is S minus M plus 1 times S plus M. And since I want to, there are of course prefactors like the dipole matrix element of a single atom, but I always want to normalize things to a single atom. And by just using the square root, if we have a single particle which is in the S equals M equals 1/2 state, then you see that this square root is just 1. So therefore, when I discuss now the relative strengths of the transitions between those eigenstates, I've always normalized to single particle. For single particle, the transition matrix element is 1. Okay, so therefore, what we want to discuss now is we want to discuss the rate, which is the matrix element squared, or the intensity of the observed radiation, relative to a single particle. So the intensity, and this is what we are talking about, is now the square root of the square root, the square of the square root, which is S minus 1 plus M times S plus M. Pretty much this is the complete description of superradiance for strongly localized atoms. It's all in this one formula. Once we learned how to classify the states, we can just borrow all the results from angular momentum addition and angular momentum operators. So I want to use this formula for the intensity and look at which is the most superradiant state, the state where all the particles are symmetric, and this is the state with S equals n, where the spin is n over 2. So I'm looking now at the ladder of M states and want to figure out what happens. So the maximum M state is M equals S. All the atoms are excited. And now the first photon gets emitted. So just put S equals put S equals M equals n½ into the formula for the intensity, and you find that the intensity gives us, this expression is just n. So we have n excited atoms, and they initially emit with an intensity which is n, and this is the same as for n completely independent atoms. So nothing really special to write home about, but now we should go further down the ladder, and let's look at the state which has m equals 0? Well, then the intensity or the matrix element squared for the transition which goes to m equals 0 has an intensity which is n over 2. I mean, just look, S is n over 2 and m is 0. Sure, we have the question whether we have an odd or even number of particles, but it doesn't really matter. What dominates is always the big factor n over 2. So what we find out is that we have an enhancement, huge enhancement over independent atom, because this intensity goes with n square. And this proportionality to n square, this is the hallmark of superradiance. So this is what is characteristic for superradiance. We have an n times enhancement relative to a single atom. So this is yes, one important aspect. Now, in the classical picture, that should come very naturally. If you have all the spins aligned and they start their Larmor precession, there is not a lot of oscillating dipole moment. But when half of the spins are de-excited, they are now in the xy plane. Now you have this giant antenna which oscillates and radiates. So it's clear that at the beginning, the effect is less pronounced, and if you are halfway down the Bloch sphere, then you would expect this n times enhancement. But now let's go further down the ladder and ask what happens when we arrive at the end. So I'm asking now, what is the intensity when the last photon gets emitted? There's only one excitation in the system, and the answer is it's not one like an independent atom. If you inspect the square root expression, you find it's n. So we have one excitation in the system, but it's completely symmetrized. And therefore, we have an n times enhancement, and I want to show you where it comes about. So there is only one particle excited, and here we have an n times enhancement. By the way, the states with the classification S and M are called the Dicke state. And this state here, which has a single excitation, but it radiates n times faster than a single atom, is a very special Dicke state. And there's currently an effort in Professor Vuletic's lab to realize in a very well-controlled way this special Dicke state in the laboratory. These are sort of non-classical states because they're not behaving as you would maybe naturally assume a system with a single excitation to behave. So let's maybe try to shed some light on it. One way how you can intuitively understand superradiance is really with the classical antenna picture, that you have n spins which form a macroscopic dipole moment which oscillates. But, and this is a very nice picture to understand the n times enhancement when we have half of the atoms excited and the other half de-excited. Let me now give you a nice argument which explains why a single excitation in the system is now leads to an n times enhanced decay. The situation is that the initial state for this last photon is we have an excited atom and all the atoms are in the ground state. However, we could also have in this nomenclature, the second atom excited, or we could have the third one excited, and so on. So therefore, what we have is, because we are in the leftmost Dicke ladder, which has the maximum S spin quantum number of n over 2, that means everything is fully symmetrized. So therefore, we have to fully symmetrize by summing over the n possibilities. And our final state is, of course, the fully symmetrized ground state. And now you realize that you have a coherent summation over, you have n contributions. So therefore, the matrix element has n contributions compared to single atom. The normalization is only square root n. So therefore, the matrix element is square root n times larger than for an individual atom. So by simply having one atom excited and n minus one atom not excited, but if you now have the fully symmetrized state, you don't know for fundamental reasons which atom is excited. You have a superposition state where the excitation can be with either of the atom. This state, which has a single quantum of excitation, radiates n times faster than a single atom would. Let me make, yes, a side remark. Maybe some of you remember when we went to cavity QED, we had just proudly quantized the electromagnetic field and we discussed the vacuum-Rabi splitting. And I told you that the vacuum-Rabi splitting is if the cavity is not empty, but is filled with n atoms because of the matrix element of the A Dagger operator, you get an enhancement of the vacuum-Rabi splitting, which is square root n, then photon number. But then I showed you the important first observation, the pioneering research at Caltech by Jeff Kimball and Gerhard Rempe, and they didn't vary the photon number, they varied the atom number, and when they had more flux in the atomic beam, the Rabi splitting became larger and larger. Well, we've just learned that when we have n atoms, that the matrix element for emitting the photon is square root n times enhanced. So if you put n atoms in a cavity filled with little n photons, the Rabi splitting between the two modes has square root n plus 1 in the photon number and square root big N in the atom number. And so the effect I've shown you in the demonstration of the vacuum-Rabi splitting, at least the scaling with the atom number, this was actually, can be understood as a super-radiant effect. Okay. So that's pretty much what I wanted to tell you about the basic phenomenon of superradiance. Now I want to discuss two more things. One is superradiance in an extended sample, and we have time for that. But I also want to discuss with you the question, let's assume we have the same system and we just convinced ourselves, yes, it's superradiant. Photons are emitted n times faster. Now, what would you think will happen when we are not looking for spontaneous emission, but we shine a laser light on it and we are asking for induced emission? Or the other way around, we ask, and you know that from Einstein's treatment it's completely reciprocal, or we're asking the question, what happens to the absorption process. So is a stimulated emission process or an absorption process, are they also enhanced n times? I don't know, do you have any opinions about that? Yes, it's a subtle way of counting. I've shown you that certain matrix element, especially the matrix element when the spin is sort of in the middle, is at 90 degrees, that we have matrix elements which are n times enhanced. And of course, if we ask for absorption or stimulated emission, we are talking to a system which has an n times enhanced matrix element. And you would say things go n times faster. Why don't you hold this thought for a moment? Now let me just wear another hat and say we have assumed that we have n independent spins. They are closely next to each other, but they're not interacting. And now I take these n spins, and for stimulated emission and absorption, we can just use the picture of Rabi oscillation. On the first Rabi cycle, we emit. On the next Rabi cycle, we absorb. So if I take now, and why don't you think about, not about these pseudo spins electronically, atoms with electronic excitation, just think of real spins which have a magnetic moment, and you drive them with a magnetic field. So now you have your n little spins, you apply a magnetic field to them, time-dependent magnetic field, and the time-dependent magnetic field is now driving the spin in Rabi oscillations. And the external drive field talks to one spin, talks to the next, talks to all of them, but each of the spins does exactly the same Rabi oscillation it would do if all the other atoms were not present. So the picture is you have an external field, all the atoms couple to the external field, but the coupling of each atom to this external field is exactly the same as of a single atom coupling to the external field. And the Rabi frequency for each atom is exactly the Rabi frequency you would get for a single atom. So therefore, based on this picture, I would expect that I have my n spins, and these can now be real spins with a magnetic moment, or can be atoms in the electronically excited state. I coherently drive them with a drive field, and they will do Rabi oscillations, but the frequency of Rabi oscillations will be the same as for a single atom. Okay, we've just held the thought that there are matrix elements in the Dicke states which are square root n times larger, and it seems the Dicke states seem to suggest something to us which would say there should be an enhancement, whereas the analysis in independent atoms which are driven by an external field also seems compelling. So now we have to reconcile the two approaches. Is the question clear? So we want to figure out, we have matrix elements in the Dicke state which suggest enhancement, but the simple picture of n independent atoms driven by an external field would say there is no enhancement. Okay, so let me just write down more formally what I explained. When we have an initial state, which is all the atoms are in the ground state to the power n, and the state n would evolve when it is driven in a state phi of t. So now the wave function for the exact wave function for our n particles is nothing else than the time-dependent solution of Schrödinger's equation for a single particle. So this is single particle. to the power n. So therefore, I mean, this is pretty much a mathematical proof, unless I've made a mistake, which I haven't. So it takes exactly half a single atom Rabi period to completely invert the population exactly as for a single atom. So that's the result. However, if you describe the system by Dicke states, you have matrix elements which are proportional to n. However, if you want to, I mean, I've sort of described it just as a two-level system. Each atom does Rabi oscillation, and I've said, okay, the system of n atoms is just n individual systems. But if you insist to describe it as a collective spin, then we have the Dicke states, then we have the n times enhancement of the matrix element, but then we also have to go through n states. So we have n steps in the Dicke ladder, and one can say now, and this is sort of the exact argument, you have n steps. You take each step n times faster, but the total time is the same. Sort of n times 1 over n is 1. Okay, but now when we talk about spontaneous emission, we are not driving the system with an external field. It's really driven by the system itself, which emits photons into the empty mode. Spontaneous emission, each step is proportional to the matrix element squared, because we're talking about Fermi's golden rule and spontaneous emission. So this is proportional to n square. And if you say that we have n steps, well, then we have n square over n. Then we have a speed up. Each step is n square faster. We divide by n, and we get the superradiance speed up, which is n. So superradiance is something which you observe in spontaneous emission, but you cannot absorb it in a driven system. Because in a driven system, you can say you have a classical external field, and this external field talks to one atom, to n atoms exactly in the same way. It is really the interference of spontaneously emitted photons which is at the heart of superradiance. As a side remark, we're talking here about a coherent effect which is n times enhanced, and you can actually regard that as a kind of bosonic enhancement in the emission of photons, because the photons are bosons. When Bose-Einstein condensation was discovered and people were thinking about basic experiments, of course, one thing which was on our mind is we wanted to show that there are processes in the Bose-Einstein condensate which are n times enhanced. For fermions, they would be suppressed. This is sort of the flip side. Big enhancement for bosons, complete suppression for fermions. And we found it, for instance, the formation of the condensate had an n times enhancement. There was a stimulation factor, but we also thought you should actually, there may be ways where you can observe suppression of light scattering or enhancement of light scattering. But we thought about it with two laser beams, Bragg scattering, and the idea seemed compelling, and then we said, no, wait a moment. If you use laser beams, everything is stimulated. You can observe bosonic enhancement and fermionic suppression only when you have spontaneous events. If you drive it in a unitary time evolution, you will not be able to see quantum statistical suppression or enhancement. And the same thing is we have seen here. When you have a stimulated system, everything is sort of undergoing a unitary time evolution, and the unitary time evolution for n atoms is the same as for a single atom. You need the element of spontaneous emission. So it may be not, I'm not proving it to you, but I'm just making it as a remark. What we have seen here, that the superradiance only shows up in spontaneous emission and not when we drive the system. A driven system is a unitary evolution, and the same conclusion which we just got for superradiance also applies if you want to observe fermionic suppression or bosonic enhancement in quantum gases. It needs an element of spontaneous scattering or spontaneous emission. Yes?
If we think of it in terms of interference of photons, how does that tie in here? Because if the stimulated emitted photons are still interfering, then you could get addition or destructive interference, constructive interference.
The quick answer is you have a classical field which you use for, you have a laser field for stimulated emission or for absorption. There are so many photons in the laser field that the few photons which your system emits do not matter. They're really talking to a classical field, and it doesn't matter whether the other n-1 atoms have emitted a photon, because you have zillions of photons in your laser field, and they determine the dynamics of the system. Okay, superradiance would not be as important as it is if it could not be observed in extended samples. So now I want to use the last 10 minutes to show you what is kept and what has to be dropped when we talk about extended samples. So let's, it doesn't really matter, but for pedagogical reasons, let's assume we have an extended sample, which is much, much longer than the optical wavelengths along the long axis of the cigar and smaller along the short axis. The second condition, that the cigar is smaller than along the long axis, does not really matter, but no, I'm not making this assumption. I'm sorry. It's a cigar, and let's just assume that everything is, just saw a contradiction in my notes. So anyway, we have now a system which is, let's have a Cuban cigar, really thick cigar. And this is now our extended sample. And what I need is, I need the cross-section of the sample A. And let's assume the length L. This is diameter D. It's a cigar is much, much larger than D. And yes, we're talking about superradiance, we're talking about spontaneous emission, but if you see a long cigar with excited atoms, you think immediately about lasing action. A photon is emitted and is amplified along the path, and of course, the preferred direction where you would expect the maximum effect to happen is when the light is emitted along the long axis of the cigar. So we want to consider now modes, preferential modes, along the x-axis. So If you now assume that you have many atoms and they emit light, if an atom here and here would emit light in this direction, it may constructively interfere, but in another direction, it will destructively interfere. But let us now consider what is the solid angle into which all the atoms can coherently emit. Well, you know that from classical optics, the emission into a solid angle of lambda square over A can be coherent. Sort of similar to when you have a double slit and you ask over what angle do the two slits emit in phase, you get a bright fringe, then you get a dark fringe, you get the next bright fringe. The coherence, the angle over which the path length differences do not add up to more than lambda is sort of the diffraction limited angle, which for a beam of size d is lambda over d, and if you take it to the second dimension, the solid angle is lambda square over d square. So that's what I'm talking about. So if you would sort of give all the atoms in your sample just the right phase, that they are coherent to emit into the x-axis, they will also coherently emit into a small solid angle, and the solid angle is given by this number. So the gist of it is, and I will not completely prove it to you, I just want to give you a taste, is that therefore we still have a superradiant enhancement. We know the superradiant enhancement previously when we had the localized system was n, but now we have the n atoms act together, but they're not acting together for emission into 4 pi, they are acting together for emission into the solid angle. And if I write the big N as density n times L times A square, the A square cancels out, and I get n lambda square L. And if you remember that the cross-section of an atom was lambda square for absorption, if the atom is excited, the cross-section for amplification of light for stimulated emission is also lambda square. So lambda square is the gain cross-section. And what we find now as a superradiant enhancement factor is nothing else like something which reminds us of a laser, which reminds us of optical gain. And actually, the lasing phenomenon and superradiance in extended samples has a lot of analogies. In some limits is even identical. I mean, we are talking about spontaneous emission. We're not talking about stimulated emission. But if we have a system which is in some excited state, superradiant Dicke states, and we're asking what are the spontaneously emitted photons coming out, to say different atoms emit into the same mode, and now you have to add up the fields coherently. This is the language we've used so far. Or if you use a language, one atom emits a photon, and this photon gets amplified on its way out. Those two languages strongly overlap, or in some limits are even identical. So the amplification of a photon on its way out, this is behind superradiance. But when we localize the atoms to less than a wavelength, well, the atoms are pretty much emits as a whole, and there is no path length of the size of the optical wavelengths where you can say the photon propagates, gets amplified. So we have looked at just what comes out of it. But in an extended sample, you could even address the question, how do the photons get amplified, magnified, augmented when they travel from the center to the edge? So you could actually ask, what is the light intensity as a function of the position within the cigar? For localized samples, you can't. So let me just write that down. So this is an analogous to optical amplification in an elongated inverted medium. Okay, so you can formally describe that. You can now define new Dicke states with respect to this, to the preferred mode, and the preferred mode is the mode in the x direction. So what I've done is, remember we have those atoms. Those atoms are now sitting at different positions, x1 and x2. And if I define Dicke states which have phase factors e to the ik x1, e to the ik x2, if now this atom emits a photon and this atom emits a photon, well, the second photon is x2 minus x1 ahead of this photon, if you think of those atoms sitting aligned in a string. But the phase factor is exactly canceling the propagation phase for the first atom in such a way that if you are now coupling these states to the electromagnetic field, the phase factors of the electromagnetic field in the mode cancel with those phase factors, and you again have the situation that each state here has an equal amplitude for emission. So now you have n possible contributions, and the normalization is 1 over square root n, and everything falls into place. And you can define that for 2 excited atoms with 2 phase factors and so on. So you can use immediately the same formalism, and what happens is those phase factors are chosen that for the interaction Hamiltonian and our interaction Hamiltonian is now different. It is di, and now in an extended sample we have to keep track of the position of the atom. So for the coupling to the mode in the x direction, we have those phase factors. So all the phase factors cancel. And actually, I'm not telling you whether this is plus or minus in order to cancel. You pick the sign that they all cancel, and then you have superradiance, you have fully constructive interference. Yes. So all this looks now the same as superradiance, but there are also things which are different, and this is the following. If the atom would emit now photons, not in the preferred mode, then remember we had sort of the Dicke ladder, we had sort of the most superradiant ladder, little bit less superradiant ladder, and eventually we had the subradiant ladder. In order of smaller and smaller total quantum number S. Emission, which is not emission in the preferred mode, stays in each ladder, and we have the superradiant cascade. But emission into other modes is now coupling different S states, because the operator or the phase factor e to the ikr has broken the complete permutation symmetry between the sides. We've changed the symmetry with not the completely symmetric sum, with a symmetric summation with phase factors. So therefore, the phenomenon is somewhat different, but we still have super-radiant cascade for the preferred mode. And the result is, is that we have an enhancement for the most symmetric, for the super-radiant states, which is given by that. And this is nothing else than the resonant optical density of your sample. So in experiments, many of them go on in Vladan Vuletic's lab, where he uses collective spin and the storage of single photons in n atoms. The figure of merit of his samples is always the optical density, the number of atoms times lambda square times the length. Finally, and sorry for keeping you 3 more minutes, the form of superradiance which is very important is Raman superradiance. So we don't have an excited state where we put a lot of excitations on, because the excited state would be very short-lived. So what we instead do is we have Rabi frequency omega 1, we have a large detuning delta, and then the spontaneous emission with the coupling constant G takes us down to the excited state. In the case that the Rabi frequency is much, much smaller than delta, we can eliminate the excited state from the description, and what we obtain is now a system which has an excited state. The width of this excited state, this is pretty much the virtual state here, is the scattering rate, which is the probability to excite the atom is Rabi frequency over detuning squared. That's just perturbation theory. And then we multiply with gamma or gamma over 2. So this is the rate of spontaneous emission out of the virtual state. And from this virtual state, we go now to the ground state. And the Rabi frequency, or the coupling for this virtual state, is the original coupling G between ground and excited state, but now prorated by the amplitude that we have mixed the excited state into the virtual state. So therefore, we have now obtained a superradiant system. And for instance, we did experiments which became classic now because their conception is so clear. We took a Bose-Einstein condensate, we switched on one strong off-resonant laser beam, and then we had a system which was 100% inverted because we had no atoms into the final state. The final state is a Bose-Einstein condensate, but with a recoil kick. So by just having a Bose-Einstein condensate and shining this laser light on it, we had now in this picture a 100% inverted system, which is the ideal realization of a fully inverted Dicke state. Everything is completely symmetric, and then we observed superradiant emission of light pulses. Okay, so this has been the important important experiments have been done with BECs in my group and with cold atoms in with laser-cooled samples in Vladan Vuletic's group. So why is superradiance so important? And this is sort of my last statement for this class and for this semester. So if you have extended sample superradiance, those samples are no longer coupling to the electromagnetic field with a coupling constant G. The coupling constant G is now multiplied by the optical density of your sample. And there is a lot of interest for current research, for quantum computation, manipulation of photon states and all that, to do cavity QED. And in cavity QED, you try to have very good mirrors, very small mode volume, to have a very, very large G. But this large G, which you achieve in a cavity, if you put many atoms in it, gets enhanced by the optical density. So the cavity enhancement and the superradian enhancement is multiplicative. And often it's very favorable for single photon manipulation if you do both. You get enhancement from the cavity and enhancement due to superradiance. And the person who has really pioneered work along this direction is Vladan Vuletic here at MIT. Anyway, yes, with 5 minutes delay, I finished the chapter on superradiance. Well, that's the end of this course. Let me thank you for your active participation. Sometimes as a lecturer, you learn as much as the students, and I think partially based on your questions and discussions, this is really true. I've learned a few new aspects of atomic physics. I hope you have learned something too, and good luck in the future.